All right. All right, so last time we talked about image models, which is fun, and there's a lot to explore there. So we talked about the few basic advancements, more recent advancements in image models. So yeah, if that's your thing, by all means, you can keep exploring those models. But now we are getting into generative text models. So today we're going to start off by discussing the foundation of pretty much every large language model that exists, every large language model that's assisting us with our work, which is the transformer model. So there are so many lectures on how transformers work online. There's so many. And so by all means, I'm not going to say that this is the best or anything, but I will attempt to explain transformer models the way I understand it. And if hopefully that captures, hopefully you understand everything based off my explanation, but in case you can't, there are plenty of videos, YouTube videos that sort of have different explanations of transformer models. I mean, the most famous one being three blue, one brown, did quite a famous series on transformer models. So you can feel free to check that out. But I think today we could power through. I could give you the aspects of transformers that I understand, and yeah, and let's see where that leads us. Today is going to be a little bit of a code. Sorry, come on, what are you doing? Okay. Today's going to be a little bit of a code lecture. That's because the homework problem tomorrow's one of the homework 10 problems is on actually writing code. It's basically coding up the transformer itself. So because of that, I don't want to spoil that problem. So I didn't really put much code in today's lecture. Today will be more about conceptual understanding. So today we're going to go over the basic transformer model. On Tuesday, we're going to go into the different types of transformer models, bidirectional, decoder only, all the flavors that make modern AI models great. And then, and I still haven't decided what I want to do Thursday and the following Tuesday. It'll be something. So let's jump right in. Where did we leave off last time with text generation, or just generative models in general? And last time we talked about generation, we were basically talking about recurrent neural networks, that you have a particular network that you can feed a sequence into, and it will give out a sequence, one or more tokens, right? And so there's a famous blog post, I think it's a blog post, titled "The Unreasonable Effectiveness of RNNs." We talked about how RNNs can be used to basically do almost any machine learning task. And a big part of that is because the inputs and outputs are scalable, right? They're not fixed. So you have a particular sequential input. You can model anything you want as a sequential input. Obviously, text you can model as a sequential input, but images also could be sequential inputs. Signals themselves are sequential inputs. So you have a sequential input, and you could get out a sequential output, or you can even, wait to input input in the entire sequence, and then take the last output and use that information for something. That's basically semantic classification. All that good stuff, right? So RNNs are pretty great, but there are problems. There's a reason why AIs didn't pop up, or at least didn't work that well prior to 2017. And the problems with RNNs, the problems with most RNNs, even the more complex ones, were that it was slow. Sequential, anytime you attach the word sequential to computing, you're going to have a bad time. No matter how fast your computer is, basically serial input and output is never a great thing. You always want to make operations parallelizable, which RNNs can't really do. Then there is the issue of the vanishing gradient, okay? So actually, I'm gonna write a little bit on the board. So the vanishing gradient issue comes because when you have a actual output function, let's say we have a df over dx, this, of course, is according to our machine learning models, this is actually equal to df over, let's say, dA, then dA over dB, then dV over dC, then dC over dD, and then all the way down until you get to a point where you have something d symbol over dx, right? That's basically how gradient descent works. Now, the issue with this, of course, is that if, let's say, the loss of these are less than 1, right? Then we have 0.5, then we have 0.5 times 0.5 times 0.5 times 0.5, all the way down to dx times 0.5. And what you get is what's called a vanishing gradient, because you're multiplying many layers of gradients together, right? This is the same thing that we saw when we were discussing visual networks also, that when you have a very deep network, it's very easy for the layers in the beginning to not have that as much effect on the layers on output, or the layers in the end to be harder to train, right? So this is what's known as the vanishing gradient. Also, some people refer to this as the exploding gradient problem, because you could have a loss that's greater than 1. So if you have a loss of 10, the average loss is 10 for each of the stages, then you get a huge number, right? So then you get an exploding gradient. So that is the vanishing gradient or exploding gradient problem. There's a very well-known paper on this. I want to, oh man, what was the author's name? Oh, Bengio, yeah. Oh, Bengio. I don't know how I forgot that. Learning long-term, he published a paper that was titled "Learning Long-Term Dependencies with Gradient Descent is Difficult." This was back in the mid-90s, right? Yeah, 1994. And yeah, so this was always a known problem with RNNs, or with any sort of deep neural networks. Just the fact that gradient descent with deep nets makes things more difficult. So vanishing gradient problem has been around for a while. It's just, it's hard to solve. So you got to figure out some clever ways to fix it. And then last thing is simply that RNNs don't have any form of attention. RNNs process a word, one word at a time. And so you're getting a word sequentially, but let's say the sequence is like, something more complex. I mean, this makes sense if the sequence was like the red dog. That's totally fine. You don't really need attention for that. Red comes before adjective, comes before a noun. The adjective is related to the noun. RNN can handle that easy, right? But what if we have a sentence, a more complex sentence, which was the mischievous dog who was also red and had a smushed face. So then that sentence is much longer, and the descriptives of the noun are in both beginning and both before and after the noun. So in that case, RNNs have a more difficult time, right? So, I mean, they have the hidden states. They have hidden states, so they could sort of try to deal with it. But in practice, it becomes a very hard thing for RNN to model complex language. So that's why if you actually train an RNN, and if you train it on a huge English data set, and then you sort of try to get something out of it, you will get some very simple sentence structures out of it, typically. And that's because this issue of a lack, I think I should say, lack of attention. Okay, so, it's a good model. The RNNs are no disrespect to RNNs. We shouldn't ever disrespect the foundational technologies that brought us where we are. But there is room for improvement over RNNs, right? And specifically, the last issue, the lack of attention, is the room for improvement. So the attention issue was a big leap was made in the attention issue when in 2017, Ashish Vaswani, oh, I'm butchering so many names, I'm sorry. Ashish Vaswani and his colleagues at Google Research / Google Brain published a paper called Attention is All You Need. And this was the first publication of what we now know as the general transformer model. The general transformer, it's actually a pretty short paper, so those of you that are scared of reading research papers, this is probably this is one of the few research papers that you really don't have much to fear on. But the thing that they published was basically they published a model which had a encoder and decoder. And what was important about this model is that it had its specific structure. It took in a bunch of inputs. It took in basically the entire sentence at once, every single word at once. And then it had a nice little, what's called a attention mechanism that allowed the model to connect the related portions of the sentences together, embed those, pass that information onto a decoder, and then work with a particular, and then do a particular task. Okay? So the big novelty of this paper is the attention mechanism. Even though this is really this is like the first introduction of the transformer, the reason it's called attention is all you need is because a transformer is basically a simple feed-forward model, but with attention layers dispersed through it. Okay. So does all that make sense? Okay. So in this lecture, we're just going to step through this little model and try to decipher each of the steps. And then hopefully once we got a hang of that, then next time we could talk about more complex iterations of the transformer model. So, transformer model. Step one. Let's start off at the encoder, at the smallest stage of the encoder. I mean, at the beginning of the encoder, sorry. Right from the inputs. And so step one will be to look at the input embedding. Okay, so first thing we're going to do is try to embed the inputs. Okay, so first thing we got to do to embed the inputs is tokenize the inputs. Machines are great at performing lots of complex operations, but they only take in numbers. They don't take in symbols. Okay, that's only us. We take in symbols. Machines take in simple, real numbers. So the question is, how do we convert a input that is symbolic into a series of numbers? So we got a lot of choices here. A lot of choices. Pretty much everything you could think of in history has been tried. Every sort of tokenization mechanism that you could think of has been tried. And so the big three are character-based tokenizations. So character-based tokenizations, basically you have, let's say you have the ASCII alphabet. Each symbol is related to a particular ASCII encoding, a numeric number. And then based off that encoding, you could give the model a series of numbers, right? So let's say we have the phrase studious students. You would convert S to the character 19. I know this isn't ASCII. This is just, I'm assuming just an alphabet of lowercase characters. And we're encoding them from 1 to 26. So S would be character number 19. So we encode that character as 19. T would be character number 20. Or ST. Yeah, character number 20. And we encode, so instead of giving the machine the letter T, we give it the character 20. U would be the character 21, et cetera, et cetera, et cetera. Okay? So this is what I'm now realizing that the first thing we talked about in the RNN lecture, I want to say, was one-hot encoding. And so this is the next step up from one-hot encoding, where basically we just encode each character as a particular number, and we just we map each character as a particular number, and then we give in a sequence of numbers to the model. Then, let me jump to word-based encoding. Word-based encoding is pretty much exactly the same as ASCII encoding, but instead of having a dictionary of characters to numbers, you have a dictionary of words to numbers. Okay, so word-based encoding is simply, you have however many words there are in your language. I think someone said that in English most people only use around 20,000 words, but you basically associate each word with a number, pass in that number for each word. Okay, so the benefit here is that you have a much larger, what's called a vocabulary size. You have a much larger vocabulary size, which isn't great because your model would have to sort of figure out word number 32,554, number 32544 is equivalent to the word studious. So that's going to be harder for the model to figure out. But it increases the amount of information per token. So the extreme here is you don't have much information per token, but you actually have a smaller vocabulary size. That makes your model smaller. It makes the computation a bit faster, easier. But you have less information per token, which harms the performance of your model. On this hand, you have the most information per token. Well, not the most, but you have a larger amount of information per token. But you have a very large vocabulary size, which makes your model computation on your model more difficult, right? And so this is not tenable because the vocabulary size is large, so you would have to have a dictionary that's huge. This is not tenable because basically there's very little information per token. So as a happy medium, this is a very NLP thing. As a happy medium, you have this n-gram-based encoding where you embed words and or sequences of characters. Okay? So an n-gram is simply a sequence of, I don't know, some tuple of characters, 3 characters, 4 characters, and then you would basically break the words up into those groups of characters. So if, for instance, you see this group dent appear a lot, then it's useful to have a token that represents that group, right? You would still, in this case, have n-grams that are just A, just B, just C. So you could get words that don't fall neatly into the other tokens like that, neatly into the other n-grams. You would have just A, just E, just C. But it's still better than the extreme case here, the 2 extreme cases. So most large language models currently, I know ChatGPT has a vocabulary size, at least GPT-3 had a vocabulary size of around 100,000. I think most models have a vocabulary size around that big. And basically that 100,000 is a mixture of common words, like the, study, etc. And common words, common prefixes, common suffixes, like us, dent, etc. And all the little characters here, S, E, A, B, C, etc. Because, for instance, when you type something into ChatGPT, like I'm an ACE student, well, it segments I in its own thing. It segments comma M in its own token. It segments ECE in the token E and CE in its own token, and then so on. Okay. So why these choices? How you tokenize language is not a science at all. And I'm sure OpenAI has spent an ungodly amount of money figuring out what the optimal tokenization scheme for every language is. Um, and so they landed on around a vocab size of around 100,000. Um, but the tokenization schemes changes between language models. You know, Llama, um, what's the Google AI? Um, Gemini, yeah. Llama, Gemini, OpenAI, all these people, all these guys have different tokenization schemes. So you have to use specifically the Llama tokenizer with the Llama model. And every time they release a new Llama model, the tokenization scheme changes again. Um, I don't know, there's no science here. It's just people just trying to optimize, something. And this is one of the few things that it's more difficult to train. Although there are like algorithmic methods to try to figure out the best tokenization scheme, but that depends on the model and so this whole optimization scheme. Yeah.
Do you use like, for like I guess really common words, especially like larger common words, do they still implement like a few word base in like an n-gram?
Oh yeah. So basically most like OpenAI is basically a combination of all of these. So most stop words, for instance, so a stop word is, for instance, something like the and something that is very common. It's just used to connect sort of the sentence together, nouns together. That pretty much every tokenizer will have tokens specifically for those stop words.
Like bigger, like I don't know, I'm thinking like because is a really commonly and like fairly large word.
Oh yeah, but it's still a lot of large words are still have their own token. Even things like, I want to say like Harry, like common names like that, those have their own tokens too also. If you want to check it out, I'm going to chat GPT tokenizer. There's a nice little online tool that I use all the time. Is this one? I am a ECE. This isn't the one I was thinking of, but I think it works the same way. Oh yeah, yeah. You could view how things are tokenized this way. So at least this is for GPT-4o. Oh, it looks exactly the same as GPT-3. Oh, interesting. But it has 200K? Yeah. Okay, yeah. So I'm more like, so again, so okay, so I guess oh man, it's amazing how primitive my knowledge becomes in just a year. So tokenization up until 3.5 turbo was 100K tokens for the vocab size, but now I guess it's closer to 200K. And you can see the way it tokenizes it, student is its own token, AM is its own token, A is its own token, I is its token. E is its own token, but CE is also its own token. I don't understand that. That is one thing that's always confused me, but this has existed for a long time.
Common
Huh?
era.
Oh, CE. Oh, that's a good explanation. Oh, maybe.
And BCE. Oh, that's interesting.
That's, let's see.
Does it factor in like capitalization at all?
So it does factor in capitalization. BCE is its own token. Oh, that could be. 80 is its own token. Oh, interesting. It could be because of Common Era. I thought it was like some weird, like there are a lot of computer engineering students like working there, and like we have to have our own token. But no, that's good. Thank you. I learned something today. All right. Well, I had fun. All right. Should we end the lecture here? I learned something. Yeah, please.
So are tokens like determined by the people who are making the model? Like do they decide? Like,
Yeah, the token is determined by whoever releases the model. So the tokenizer is set beforehand. It's basically a large dictionary. And how the tokenization, I mean, there are research papers on like on optimal tokenization schemes and all of that, but I don't think there's no ground truth. And because it's also model dependent. How your model is structured affects like how big your vocab size should be, and then how big your vocab size should be affects like how your model is structured. And then you have this third thing, which is if your model is optimized, for instance, like there's thousands of different like GPT flavors, right? I mean, when I make my TXC figures, sometimes I use the TXC one. So I'm sure for every ChatGPT flavor, they change the tokenization scheme to be better for that. So, yeah. Did you have a question? Yeah,
Yeah,
please.
I think I know the answer to this, but
Yeah.
are spaces also included in those tokens?
Um,
I guess they would have to be,
yeah, I mean, I don't know.
Looks like, I mean, because like
Well-
AM, like you're not gonna have. I don't know.
Oh, that's a good question. I just assumed spaces were. Oh, they are separate tokens. Oh, I guess. Oh, that's an interesting.
Tokens for like a space before and a space after.
Yeah, yeah. I guess you have separate tokens for with a space and without a space. I don't know where that would come up though. Oh,
Well, I guess like am and like amber.
I wonder.
Them could be treated the same. Space on its own.
Oh, space on its own, like multi-spaces on it. Like, okay, so this is all one long space, but students on its own, that is a. Yeah, that's a separate. Oh, well, no. Token, students, token IDs, top 5 most frequent tokens, frequency 2. Oh, this is the same token, but then how do I do, oh, I know. Oh, I know how to test. ECE versus, there we go, CE. Are these separate tokens? Yes, these are separate tokens. Very interesting. Yeah. Yeah.
What if you take the space away after the student and then just students?
Well, if you do students, it says that, so it says student 2. If you do student, oops, I steep go. Yeah, this is how we're going to spend our entire lecture. Well, it was interesting. But yeah, it is 2 different tokens, basically. Although that sort of makes sense. Well, actually, no. I guess because if it doesn't have a space before it, the student here, instead of being like its own word, becomes part of another word. So I guess you have to have a separate token for those 2 cases. Yeah. I'm surprised that there is a token for a token separation between these 2. I would have thought that there was only going to be that one token. But there is some ABCD. If you do, well, ABC is its own token, but D becomes its own token. There's a lot of nuances here. So yeah, by all means, have fun with this. Yeah, but this is basically every model has its own tokenization scheme. If we change to, for instance, let's go to turbo, which is a little yeah, nothing has changed here. Yeah, I don't know where the extra 100K tokens are coming from. That might be a good thing too. Maybe I'll look into it. Okay, good. Yeah, so tokenization is simply the art of breaking up a language into chunks and then mapping those chunks to a number. Okay, and the numbers don't have to be close together or far together. They have no relationship with each other. It's just you know that you have 100,000 chunks. And then you just go down the line. Here, 1, 2, 3, 4, 5. Okay, good. So let's talk. So let's assume word tokenization. So let's just, for the sake of visual clarity, we're just going to assume word tokenization for the time being. And so, looking at word tokenization, we have a sentence. We have a sentence here. So then the tokenizer takes each of those words in the sentence and outputs a number. And then when you output a number, you output a number. That number corresponds to a column of what's known as the embedding matrix. Okay? So, again, everything in machine learning is a vector or matrix, right? Well, vectors are matrices. Everything in machine learning is a matrix. So, why do we embed? Why don't we give the machine learning model this instead? Why do we give it this instead of just this number? And the reason is because, well, when we input in a particular word, we want to give the model some information about what the word means, right? Right now, these numbers, they contain no information about what the word means. The model has no semblance of knowing what graduated means, what honors means, what with is. All these numbers are pretty much equidistant from each other, right? But that's not ideal. That's not how language works. We know that certain words are closer together, like students and studious are closer together than you know, with and graduated, I don't know, or graduated and honors, right? Those two are closer together. Studious and student are closer together. Honors and students could be close together, or they could be far apart depending on the student. So the question is, we want to give the machine learning model that information. We want to give the machine learning model the information we as human beings have, which are certain words like cat and dog are more related than other words like dog and table. So what we do is we want to develop a way to encode semantic information into the input we give the machine learning model. And so the way we do that is through an embedding, right? Same way, you know, when we did convolutions, after doing a bunch of convolutions, those features sort of embedded some particular aspects of the original image. Same idea here. We want to convert this number into a big vector so that this vector contains some information about the original word. Okay? Now, the question is, what should this vector be? And that vector is for the actual model to decide. Okay? This vector is a trainable parameter. So we have what's known as an embedding matrix. And this embedding matrix has the size of whatever, we call this the model size or the embedding size. So let's say this model size is 512. So it has 512 rows, and it has whatever the vocab size is, 200,000 columns. Okay, so each of these columns relates to a particular word or token in the vocabulary. Okay, so we start off with a bunch of random values in this matrix, right? And then as time goes on, as we train, the model will slowly see, hey, the words student and studience often appear together, so I'm going to try to make the distance between the embeddings of student and studious closer together. Okay? So the model will sort of, as it sees more data, and as you train it, it will try to make the embeddings contain more and more semantic information. And so there is that classic and queen's example, the queen versus king example that people, like machine learning people, like to tout all the time. That basically you have a embedding for king, and the embedding for king minus the embedding for man is equal to the embedding for queen minus the embedding for woman, right? That sort of thing. Well, the reason that happens is because if the model is trying to embed some semantic information into it, so it might see that, for instance, the word king appears in the context of he and him a lot, and also in the context of royalty a lot. So he'll see, okay, I gotta combine sort of the embeddings for man and the embeddings for royalty for this new word, which is king. Okay? So as you're training the model, it's updating this embedding vector, or embedding matrix. Okay? So this embedding matrix stays consistent for, well, I mean, once the model is trained, this embedding matrix stays consistent, although every time you do train it, it depends on what you're doing. Sometimes you want to update the embedding matrix, sometimes you don't. But once the model is trained, once you sort of train it on, let's say, all of English literature, then your embeddings here will contain semantic information about each word and will allow you to, if you do a quick distance measurement, the distance between the embeddings for dog and cat will be shorter than the distance between the embeddings dog and table. Does that make sense to everyone? So this is a classic embedding. This is a classic embedding, the embedding problem that is very common in NLP. The only difference here is that this is just one aspect of the model. This is like, in natural language processing, prior to the large spread proliferation of proliferation of different, like, you know, transformers or RNNs, or even linear networks, you tried to create these embeddings using some deterministic algorithms. That, I mean, none of them were unsuccessful, but it turns out that this method works much better. Okay? Just give the model some space, some random parameters that it could train, and then eventually, as it goes through the training process, it'll figure it out. Who knows how? It's machine learning. Yeah.
What does each like value in the matrix represent?
That's just some garbage data I populated a matrix with. But I mean, there is no real way to like look. I mean, if you try, so there's a reason why pretty much every video you see online will discuss these things conceptually. It's because you're going to get a series of number in the embedding matrix. Let's say you download the pre-trained model from PyTorch, one of the BERT or one of the BERT models. You could look inside the embedding. You could look inside the embedding matrix. You could see a bunch of values here that have been pre-trained. I don't think anyone could possibly decipher it. It's just a bunch of numbers, and we know it contains semantic information about what the words are because if you relate them to each other, again, you can see the embeddings for certain words that seem more connected to each other are closer together. But beyond that, there is no real way to sort of decipher this number relates to like gender. Those sorts of things, I don't think even are contained inside a single number. It's probably some weird combination of things, like genetics, right? It's like each of those like little genes, there's like 4 or 5 possible values, and then, but if you look at a specific gene, you can't say like, oh, this gene is on, therefore I'm going to be 7 feet tall. It's like a whole combination of things that come together. So that's probably what's happening there. Although I do wish someone could come out with like a really good paper that's like, yeah, that's the pattern, if it exists. Yeah, please.
So is the size of the matrix height, like, is that just arbitrarily chosen?
Yep, the size of the matrix, that's what we refer to that as the model size. And yeah, that's arbitrary. So 512 is the one that they used in that Vaswani used in the Transformers paper. I don't know what the model size is for current GPT, but I think it's huge. It's definitely in the like tens of thousands, not hundreds of thousands. Yeah, it's much larger, the model size. And yeah, you wonder if there's even that much semantic information in words, but like in the English language, I mean, at a certain point, I would imagine there's not much use for making the embedding sizes ever increasing. But apparently, I'm wrong. So OpenAI, like every model, the model sizes get larger and larger and larger and larger, and it's kind of insane. And that's also one of the reasons why you pretty much need a very, very beefy GPU to run these models anymore. Just the embedding matrix alone is huge. Okay. Good? Does that make sense? Embeddings? Okay, so the next thing, I mean, most of you have probably seen embeddings before, but you probably haven't seen positional encodings before. So positional encodings, one thing that, positional encodings had been discussed prior to this paper, but this paper had a new, oh, no, this picture is too big. Okay. This paper developed a new type of positional encoding, which made things work much better, although it made things also much clearer. But let's just go into the core concept behind positional encodings. Positional encodings exist because we want a method to reference a word at a particular position in the sentence, okay? We want the model to be able to see this word is in this position, okay? So one thing that isn't great is if you don't give a positional encoding, then what happens is that, on one hand, the relation between the rows can help the model a bit, but it becomes very hard for the model to sort of remember, like this word comes after this word, and the other word occurs like 2 or 3 words down. It becomes very hard, okay? Because these are matrix times matrix multiplications, and sort of as you do matrix times matrix multiplications, the positions of each of the words and stuff, it sort of gets lost, right? Row times column, column times row, all of that, things get mixed up, added together. So the position so the position of different words gets lost. So the important thing that isn't unique, the important thing that people have been trying to do prior to this paper is try to embed the position of a word within a sentence in the actual embedding of the word, okay, in a useful way, in a way that works, okay? So there are a bunch of different types of positional. So how do we do that? Well, at least in this particular Transformers paper, what they did was they started off, well, they got the embedding. There we go. Come on. There we go. We had the embedding, and then we had some particular position encoding. We made the position encoding the same size as the embedding, 512, and then we added the two together to get the full encoding of each word. Okay? So the first word would have a particular embedding. It would have a particular position encoding. Then you would add these two together, okay? And what's important is that these position encodings are the same for, it would be the same value for a word in the same position for all sentences, right? So for the first word in every sentence, they would have the same position encoding. That's kind of an important thing also, because you don't want to keep recalculating the different position encodings. You don't want the position encodings to be different for every single sentence because, well, A, you want to save that compute power. And B, like if the position encoding is different for every single sentence, then the model's not really learning positions, right? It's learning some other random crap. It's just learning something else. It wants to be able to, this position encoding has to be consistent because it wants to be, the model has to learn. These values correspond to this word is the first word of the sentence. Okay? So the question now is, how do you get this position encoding? How do you encode a particular word inside a position, let's say inside a vector of 512 real numbers? And so the answer that the Transformers model gave, zoom out, there we go, is that you use sinusoidal functions. You use alternating sinusoidal functions, okay? So you develop a function that takes in, you have a function that takes in a position, the actual integer position of the word inside the sentence, so 1, 2, 3, 4, 5. And then you have the number of dimensions, or actually you have the index of the dimension, and this is the number of dimensions of the model, so we're using 512 in this case. So for each value of the vector, and each position in that position encoding, each value in that position encoding, we put in the position of the word within the sentence, and then we calculate this function, which is the sine of the position over 10,000 to the 2i over dimension of model, okay? And then we put that vector, and we put that value here, okay? And then what's unique here is that for the next position, for the next number, we do the cosine, okay? And then we switch back to the sine, and then we switch back to the cosine, okay? So POS is the position in sequence, I is the embedding dimension, and D is the total embedding size, so the 512 that we were using, okay? And then even dimensions get the sine function, odd dimensions get the cosine function. Now, I know a lot of you are looking at me and are like, where the hell did this come from? I have no idea. I genuinely have tried so hard to get the rationale behind this. And as far as I could tell, there is no straight derivation for this. This is something that came out with this paper. And I looked at the author's previous papers, and I didn't see anything related to this particular thing in their previous papers. So yeah, someone will have to find them and ask them. Yeah, if anyone could hunt Vaswani down, please, this is the one question I want. How did he derive this positional encoding? But but the reason that this works, and here are some theories. Here are the explanations that people always give for the reasons that they work. One is that the core reason for using sinusoids is that they encode both absolute, that sinusoids are both smooth and periodic. So for instance, you have, if your sentence, I mean, we're using 512, right? If your sentence is more than 512, let's say it's 1,000. I mean, let's say we're not doing one sentence, we're doing an entire paper, right? And we have 1,000 words. We don't want something that is constrained to like the size of the model, right? So we have to have some function where we could encode larger context than the size of the model, right? So we can't just do a one-hot encoding, which would be really nice. That would be my initial thought. So we need some function. We need some smooth function. So sinusoids are generally good in that respect. They're smooth and periodic. And then they encode both the absolute position and relative distance to each other because, I don't know why it's all jumbled like this, because you could easily compute the relative offsets of the sinusoids using this identity. Okay? So if you're able to, if each different dimension has a different frequency, you could, the low frequency captures long range patterns, the high frequency captures local patterns. And in the paper, they specifically say they use sine and cosines at different frequencies, and for each position, they generate a vector whose indices are sine functions and whose odd indices are cosine functions of different wavelengths. Okay? So what they're doing is that in their position encoding, they're actually, each different number, each dimension is related to a sinusoidal function of a different frequency. And putting that together, adding that to the original embedding, remember, we're not giving the model these values on its own. We're actually adding these to the original embedding. This allows the transformer to work backwards, to extract the frequencies contained within this vector and get the actual position. Okay? So that is as good of an explanation as I could possibly give. And I know it's a very unsatisfying explanation. Basically, the best thing I could tell you is that it just works well. There we go. It just works well, and it works well because the sinusoids are encoding the position in a summation of different frequencies, and doing so gives each position vector basically a different pattern. And then the transformer model is able to pick up on that pattern. Even though it's added to the original embedding, it's still able to pick up on those perturbations in the original embedding and extract the position of the words. Okay? So this isn't the only type of position encoding. There are many, many types of position encodings, even before this paper, both learned and fixed. Fixed would be something like one-hot encoding. But there was this concept of learned position encodings that was quite popular before this paper. But of course, Vaswani did do an analysis where he compared the learned position embeddings to these sinusoidal position embeddings, and found that there was very little difference. And so if there's very little difference between a deterministic model and a trained model, then you should just go with the deterministic analytic model. Right? So that's how the position encoding of these different of the model works. But what's most important is that you remember you go from word to tokenization to embedding. You add the positional encoding to that embedding, and then you're finally left with the input vector to the model. Okay? It's a trip. It's a whole thing. But this matrix right here, basically the D model size times the number of tokens in the sequence, that is the input to the transformer model. Okay? So now that we have the input to the transformer model, the next step is attention. And specifically, we are interested in a multi-head attention, although let's start off with just simple self-attention. Okay? So attention itself is a mechanism that allows the model to focus on different parts of the input when producing a particular output. Okay? So ideally, we want the model to look at a sentence, like here, and see, okay, the word studious is related to the word student, and the word studious is related to itself, of course, and it's not super related to the word with, okay? So we want basically a matrix that gives you values that correspond to how much a particular word corresponds to another particular word, okay? So in order to do this, the attention mechanism they propose is called scale dot product attention, and it is the combination of three different matrices: the query vector, the key vector, and the value vector. Okay? So what do these vectors? So in the encoder, each of these I shouldn't say vector. These are matrices. Well, anyway, the query matrix, key matrix, and value matrix. Okay. So in the encoder stage, each of these values is equal to this matrix here, okay? The input matrix we got before by taking the embedding, adding the positioning encoding, that is of size model dimension times sequence, that is equal to Q, K, and V, query, key, and value, okay? So the formula that we do is that the attention is equal to the softmax of the query times the key transpose normalized by this scalar times V. So let's just take this step by step. The query times the key transpose. This is a, oh, I guess I flipped the dimensions around. That's okay. This is a 7 by 512 matrix. Then we multiply that by a 512 by 7 matrix. That's error there. We multiply that by 512 by 7 matrix, and then we divide that by a scalar. So what is dividing these two together get? We get a 7 by 7 matrix. And we get a 7 by 7 matrix where, ideally, each of these values corresponds to how related one word is to another, okay? And we're going to add in some weights and trainability in a minute. So if you're like, how does that work? Well, each of these embeddings contain semantic information that when multiplied by each other could do this, but also we'll add in some extra training in a moment. But we could take the multiplication of this, and then we'll pass it through a softmax, where the softmax makes each row total equal to 1. Okay? So what happens in this case, where each row is total equals to 1, is that once you pass each row through the softmax, you get a series of values which say the is related to studious, it's related to student, more than it's related to with. Okay? You get basically a attention matrix. Okay? And once you have this attention matrix, you multiply this by, oh, that's an error too. You multiply this by the value vector, to weight the inputs, to weight the inputs, so that certain inputs that are more related to each other are weighted more heavily, and certain inputs that are not weighted, that are not really weighted together, are weighted less heavily. Does that make sense? So once we do, so this is the idea behind attention. We multiply Q, the query, times the key to get basically normalization, like a curve, a distribution where a distribution that tells us what words are most related to each other within the sequence. And then we multiply that again by the input sequence to basically weight the input sequence so that the words that are, so that the embeddings of the words that are more related to each other are larger than the embeddings of the words that are less related to each other. Okay? So that's the basic idea behind attention. There are some nuances. So an example of this, you could do a little analysis. So this is in the original Vaswani paper. That you could do a little analysis of this, and if you look at attention, you will see, if you look at the attention matrix, you will see certain words like, you know, in the sentence, the law will never be perfect, but its application should be just. In that sentence, you see the law and its being strong, having a larger weight, because presumably these are very related to each other. Okay? And it's useful because you could actually see that the model is sort of understanding it's referring to law and no other tokens. Okay? All right, but the attention that is used in the Vaswani paper is not that simple scaled out attention. It is what's known as multi-head attention. And the multi-head attention is almost exactly the same as what we just discussed, except that for the query, key, and value, we actually multiply it by a weight matrix to get, and actually this should be a model by model weight matrix, sorry, not a sequence by model, a model by model weight matrix to get just get a Q prime, okay? This weight matrix is just, again, a tunable parameter, helps the model learn whatever. Okay? And then what we do here is that we break the matrices. Remember, this is a 7 by 512 matrix. We break these up into, let's say, 4 parts. We break each of these vectors up into 4 parts. We do the multiplication, multiply Q times K transpose, divided by the square root of the we multiply Q times K transpose, normalize, then put that into a softmax function, and then multiply that by V. That is what's known as one head. And we do that for the other portions of Q, K, and V. Okay? So this is what's known as multi-headed attention. And the reason this works, so there is a question of why we're doing this, right? Because mathematically, this seems like pretty much exactly the same as if we just, I mean, yeah, we added in some more trainable parameters, but why do we have to break it up? Because if we broke it up and we're just doing the same computation, then once we have all the different heads, we combine the heads again and then pass it through another output parameter. It seems like the computation is exactly the same as if we kept everything large, right? What's the difference? Yeah. It is faster. There's an aspect of it being faster. Although with modern, there are modern algorithms that are able to break matrix multiplications up into little parts. So the speed isn't amazing. The speed up isn't amazing. Although I do think there will be some speed up. But the computation isn't exactly the same as if we just did it with the larger models. What's the difference in computation? Yeah, Ben.
Like when we're computing gradients in order to learn, there's distinct different results.
Yeah.
Whereas if it was all grouped into one result, it would all be like one gradient. Like breaking it into different gradients for each item.
Yeah, you're so close. Basically, there's an extra little term here that's not there. The extra little term is softmax, right? Over here, if we kept all of these big, it would take the softmax of that entire 512, right? But because we broke it up into 4 parts, you take the softmax of these two, you take the softmax of this multiplication, softmax of this multiplication, softmax of this multiplication, and then you combine it together. So that extra, those extra nonlinear activation functions break up the computation, right? Same thing as we remember we talked about constantly that we have to break up every weight matrix. We have to shove in some nonlinear activation because if we don't, the weight matrices could just be combined and form a new weight matrix, right? In this case, same thing, but remember that the formula for attention is softmax of Q times K times V, right? So in this case, if we kept it one large matrix, we would do softmax of Q times K times V, but that would be a single softmax for the whole thing, right? In this case, we're doing softmax of Q1 times K1, and then basically we're breaking and then we're timesing it by V1. So we're breaking the dimensions into 4 and separating it out from these other heads, right? So the model has a better opportunity of devoting each head to a different aspect of the language, right? Maybe one head is looking for adverbs, another head is looking for adjectives, maybe another head is looking for prepositional phrases, et cetera, et cetera. Okay? So those extra little linear activation layers end up making a big difference. Okay? So that's what multi-head attention really is. It's just shoving a couple extra activation layers into the computation so that the model could segment the processing up and look for different aspects of the language. And this is 4 heads, but I mean, I'm sure GPT has thousands of heads going for it, using thousands of heads, or if not hundreds of thousands. Does that make sense? Okay. So that's how multi-headed attention works. And again, there's a good way to visualize this. They give an example in the paper where you have multiple heads. Each of these colors corresponds to a different head with the actual opacity corresponding to the value of the attention. And you see that, for instance, one head connects making with difficult very well. Another head is connecting more with difficult. So one head is connecting adjectives with or adjectives and adverbs. Another head is connecting different nouns or verbs with adverbs, that sort of thing. So each of the heads gets trained to do some different thing. Similar to how in a convolutional neural network, each of the filters gets trained to look at a different aspect of the picture, right? All these concepts are related. You basically give the model more space and more segmented space, and each of those segmented spaces starts looking for a different thing. Make sense? So attention is actually the hardest thing to understand with these transformer models. So by all means, you can either watch the recording again or look up some other videos, but eventually it will click. Look up some explanations, eventually it will click. Okay, so the rest of the encoder is pretty standard. You go from the multi-head attention, you add it to the original input embedding. You add it, you normalize it. Remember that batch normalization step? That's very present here as well. Then you pass all of this, again, to a feed-forward network. Then you add it. Then you add the input and output of that together. You again normalize it. So all of these things we have seen before. And again, the linear layers are trainable. The normalizations have 2 trainable parameters. So the model just learns something. So all of that, and that is basically your embedding, your encoder. So your encoder will output a sequence length times the model dimension size matrix, where every row is a vector of size model dimension, and that corresponds to some semantic information about the sequence, about that token, and about how it relates to the sequence as a whole. Okay? So, where? That doesn't make sense. Okay, I don't know where the settings for these went, but let's just go through to Python. That was supposed to be, all of these are supposed to be slides. Well, whatever. So now we have the decoder. The decoder is almost exactly the same as the encoder, but the decoder is almost exactly the same as the encoder, but it has two differences. One is the masked attention. It's simply the idea that you could, the masked attention is simply the idea that in the decoder stage, a decoder is supposed to get a sequence in token by token and output a sequence token by token by token, right? So what you don't want the decoder to do is if you have a sequence of, let's say, the student graduated with honors, if the decoder is supposed to output the sequence, it can't look forward. It can't look forward and say, and see that, okay, there's a student here, so I should output studious right now. It should be, deterministic. It should be forward. It should only be able to look forward in time, not in the future, right? So because of that, the attention for these values should be negated, okay? The attention for the values forward in time, in the future, should be negated, so the decoder can't look forward in time. And so the easiest way to do that, this is softmax. So basically, you want to pass these through a softmax function. So the easiest way to make these all 0 is to simply make them negative infinity. That way, this will be the biggest value, and all of these will be small, tiny values. So you'll end up with 1, 0, 0, 0, 0, 0. Right? That's just how softmax works. Okay? So this is what's called a masked attention. You just basically multiply this layer by a mask. Or you add the mask to this layer, and this mask is literally zeros here, so we're preserving the original values, plus negative infinity here, or negative some unbelievably large value, and then you get this masked attention. So that's one aspect of the decoder that's different. The other aspect of the decoder that's different is cross attention. Cross attention. If we look at this model again. We see that the embedding, the stuff we calculated in embedding, has to come into play somewhere. And the place it comes into play with is in the attention mechanism. Okay? So we have one attention mechanism in the decoder that's as normal. That's the same as the prior attention mechanism, but masked. But now we have another attention mechanism. And the new attention mechanism is simply trying to take information from the encoder and use it to determine what parts of the decoder input I should actually care about. Okay? So because of that, we need the output of the encoder to go into some inputs of the attention here. And specifically how they do it in the Vaswani paper is simply that the key matrix and the value matrix come from that encoding matrix. Okay? And the query matrix is the decoding matrix, is the decoding input. Okay? So what happens when you do this? Well, it means that you get the queries for each of the rows in the queries. It's multiplied by the encoder, which has information about, the embedding, whatever was the input, the actual, what you need to pay attention to. So you multiply those together, you get a vector that's like, okay, based off this input into the decoder and what we got from the encoder, you need to pay attention to these values from the encoder and use those values from the encoder to combine it with the decoder input to generate a new output. Does that make sense? Okay. This will make sense if we look, I know I'm out of time, but this will make sense if we look at inference. And so, inference, this is how inference works. let's say we have a question answer task. Let's say we have a question and answer task in this, and we want to use transformers to answer it. Okay, so the input to our model is start a sentence. There's always a token that represents the start of a sentence. There's always a token that represents the end of sentence. Okay, so let's say the token we have a task that says start a sentence. Mary had 3 apples but ate 1. How many does she have now? And so we put this sequence into the transformer. We get an actual matrix from the encoding. We get an actual matrix. Sorry. From the from the encoding layer. We feed this sequence into the encoding layer. We get an actual sequence times the dimension of the model encoding matrix. And then we pass that value into this multi-head attention. And then what we need to do for the decoder, we need to prime it. Okay? We need to prime it, so it needs to generate some values. So we start off by having a start a sentence token, and having the decoder go through and generate the next value after start a sequence. It's going to actually generate the word. It's going to guess the word Mary. Then after that, we're going to have the decoder go through and generate the next word. It's going to generate the word has, and so on. So what is it doing when it's generating the next word? It's looking at the previous words it's already generated. And then we go through the decoding stages up until we get to the softmax layer. And then once we get to a softmax layer, we get a probability distribution for every single word in the vocabulary. And based off what words are most probable, then we actually take that word and we add it to the sequence the decoder has generated. So in this case, we have generated start a sentence, Mary has so far. So we go through the decoding step. And so we go through the decoding step. At the softmax, we look at all the vocabulary words. And so for some of the words, there's going to be almost no probability, like banana. Mary has banana, doesn't make a lot of sense, so we're going to say 0.01. It's going to be a low probability. But then for some of the numbers, there's going to be a higher probability, right? So the higher probability number, we could just choose that number and add it to our sequence. So we go from start a sentence Mary has to Mary has 1. And that will be our new sequence. And then if we want to generate the next sequence, we put Mary has 1 into the input here. We keep the embedding the same. The embedding vector stays the same, and then we generate the next probability distributions for the vocab space. Okay? So that's how inference works. I know that's a lot to take in. So next time, I think what I'm going to do, I'm going to spend a little bit more time discussing training and inference on this, and go over the transformer model one more time, really quick, to make sure everyone has it down. But hopefully this has whet your appetite. This has sort of sparked some thoughts. And next time, if you have more questions, you can ask me. But yeah, so that's the beginning of how the transformer model works. Come on. My trackpad says stop working. It's old. Okay. So we're going to talk about inference and training more tomorrow, but that's it for today. The project descriptions, I mean, they're actually updated. I think they're updated on my overleaf. I have to update the GitHub drive, and I'm going to update the website today/tomorrow. And homework 10 will be assigned tomorrow. And most importantly, have a good weekend. Yeah, so keep an eye on Piazza. All right, thank you guys. Have a good day.
For the final assignment, am I allowed to